A solar system is a collection of objects held together by gravity. At the center is a star. Orbiting the star are planets. Alongside planets are moons, asteroids, comets, and dust. All of these objects follow predictable paths. Gravity keeps the system organized. Our home system is called the solar system. It formed approximately 4.6 billion years ago. The solar system formed from a large cloud of gas and dust. This cloud is known as a molecular cloud. Gravity caused regions of the cloud to collapse. At the center, material collected and heated. A young star formed. This star became the sun. Remaining material flattened into a rotating disk. From this disk, planets slowly formed. Gravity is the force that shapes the solar system. It pulls matter together. It keeps planets in orbit. It stabilizes long-term motion. Without gravity, planets would move in straight lines. With gravity, they follow curved paths around the sun. These paths repeat over time. Planets move around the sun in elliptical orbits. An ellipse is slightly oval. Most orbits are nearly circular. Each planet completes one orbit at its own pace. Closer planets move faster. Farther planets move more slowly. This pattern creates a stable rhythm. Most planets orbit within a flat region called the ecliptic plane. This plane formed from the original rotating disk of material. Because the disk was flat, planets formed along the same plane. This creates an orderly arrangement. Distances in the solar system are vast. Astronomers use astronomical units, or AU. 1 AU is the distance between Earth and the Sun. Earth is 1 astronomical unit from the Sun. Neptune is about 30 astronomical units from the Sun. Light from the Sun takes about 8 minutes to reach Earth. Light takes several hours to reach the outer planets. The Sun contains over 99% of the solar system's mass. Its gravity dominates the system. All major objects orbit around it. The Sun's energy drives planetary temperatures. Its radiation influences atmospheres. Its presence defines the structure of the system. The solar system is divided into regions. The inner region contains rocky planets. The outer region contains gas and ice giants. Between them lies the asteroid belt. Beyond the planets are distant icy regions. This arrangement reflects temperature during formation. Close to the Sun, temperatures were high. Only rock and metal could solidify. This produced Mercury, Venus, Earth, and Mars. These planets have solid surfaces. They vary in atmosphere and temperature, but they share rocky composition. Farther from the Sun, temperatures were lower. Ices and gases could accumulate. Large planetary cores formed. These cores attracted thick atmospheres. This produced Jupiter, Saturn, Uranus, and Neptune. These planets are mostly gas or ice. Planets rotate on their axes. This rotation creates day and night. Rotation speeds differ. Some planets rotate slowly. Others rotate quickly. Most rotate in the same direction as their orbit. Most planets tilt slightly. Tilt affects seasons. Greater tilt creates stronger seasonal changes. Smaller tilt produces milder seasons. Earth's tilt is about 23 degrees. This tilt creates spring, summer, autumn, and winter. The solar system has remained stable for billions of years. Planetary orbits change very slowly. Major disruptions are rare. This long-term stability allowed planets to develop distinct characteristics. In addition to planets, The solar system contains many smaller objects: asteroids, comets, meteoroids. These are remnants from formation. They provide clues about early history. Many planets have moons. Moons vary in size and composition. Some are rocky, some contain ice, some may hold subsurface oceans. Moons are common throughout the system. Beyond Neptune lies the Kuiper belt. This region contains icy objects. Farther still is the Oort cloud. The Oort cloud surrounds the solar system. It is the source of long-period comets. The solar system is one of billions of planetary systems. It exists within the Milky Way galaxy. Its structure follows physical laws. It is neither unique nor unusual, but it is the system we inhabit. Studying the solar system helps scientists understand planets. It provides a reference for other systems. It reveals how planetary systems form and evolve. It offers insight into Earth's history. The Sun is a star. It is a medium-sized star located near the outer region of the Milky Way galaxy. Like all stars, the Sun is a massive sphere of hot gas. Its primary components are hydrogen and helium. The Sun formed approximately 4.6 billion years ago. It has remained stable for most of its existence. The Sun contains more than 99% of the total mass of the solar system. Because of this, its gravity dominates the system. Planets, asteroids, and comets orbit the Sun. Without the Sun's gravity, the solar system would not exist in its current form. The Sun acts as an anchor for all major objects. The Sun's diameter is about 1.4 million kilometers. More than 1 million Earths could fit inside the Sun. Despite this size, the Sun is considered average compared to many other stars. Some stars are much larger, others are much smaller. The Sun has several layers. At the center is the core. Surrounding the core is the radiative zone. Above that is the convective zone. Beyond the surface lie the photosphere, chromosphere, and corona. Each layer has different properties. The core is where energy is produced. Temperatures reach about 15 million degrees Celsius. Pressure is extremely high. Hydrogen atoms fuse together to form helium. This process is called nuclear fusion. Fusion releases large amounts of energy. This energy eventually reaches the surface as sunlight. In fusion, small atomic nuclei combine. When hydrogen nuclei fuse, some mass is converted into energy. This follows Einstein's equation, E equals mc squared. Even tiny amounts of mass produce enormous energy. This energy powers the Sun. Energy moves outward from the core. In the radiative zone, energy travels as radiation. In the convective zone, hot material rises and cool material sinks. This slow movement carries energy toward the surface. The process takes thousands of years. The photosphere is the visible surface of the Sun. Its temperature is about 5,500 degrees Celsius. This layer emits the light we see. Sunlight takes about 8 minutes to reach Earth. Sunspots are darker, cooler regions on the surface. They are caused by magnetic activity. Sunspots appear and disappear over time. The number of sunspots rises and falls in an approximately 11-year cycle. The Sun has a strong magnetic field. Magnetic lines twist and move. This activity creates sunspots, flares, and prominences. The magnetic field changes slowly over time. Solar flares release bursts of energy. They emit radiation and charged particles. Most flares do not affect Earth. Large flares can disturb Earth's magnetic field. Earth's atmosphere provides protection. The corona is the Sun's outer atmosphere. It extends millions of kilometers into space. It is much hotter than the surface. Temperatures reach millions of degrees. The cause of this heating is still being studied. The Sun constantly releases particles into space. This flow is called the solar wind. The solar wind shapes planetary magnetospheres. It interacts with Earth's magnetic field. This interaction creates auroras. The Sun is about halfway through its life. It is expected to shine for another 5 billion years. Eventually, it will exhaust its hydrogen fuel. It will expand into a red giant. Later, it will shed outer layers. Its core will become a white dwarf. The Sun is a stable star. Its energy output changes slowly. This stability allows long-term planetary climates. Life on Earth depends on this steady output. Distance from the Sun determines how much energy a planet receives. Closer planets are hotter, farther planets are colder. Atmospheres modify these temperatures. The Sun sets the baseline. The Sun orbits the center of the Milky Way. One orbit takes about 225 million years. The Sun moves together with nearby stars. This motion is slow and stable. The Sun provides light and heat. It anchors the solar system. It drives weather and climate. It makes Earth habitable. Understanding the Sun helps scientists understand other stars. The inner solar system contains 4 planets: Mercury, Venus, Earth, Mars. These planets orbit close to the Sun. They formed in a region where temperatures were high. Only rock and metal could solidify. As a result, these planets are dense and rocky. They are known as terrestrial planets. All inner planets have solid surfaces. They are composed mainly of silicate rock and metal. Each has an iron-rich core. They vary in size, atmosphere, and surface conditions. Despite differences, their overall structure is similar. Mercury is the planet closest to the Sun. It has a small size. Its diameter is slightly larger than Earth's moon. Mercury has almost no atmosphere. Because of this, temperatures vary widely. Daytime temperatures can exceed 400 degrees Celsius. Nighttime temperatures can drop below -170 degrees Celsius. Mercury's surface is heavily cratered. It resembles the Moon. Large impact basins cover much of the planet. Cliffs and ridges indicate that Mercury has shrunk slightly over time. The planet has a large iron core relative to its size. Mercury orbits the Sun in about 88 Earth days. It rotates slowly. One day on Mercury lasts about 59 Earth days. Mercury has a 3-to-2 spin-orbit resonance. This means it rotates 3 times for every 2 orbits. Venus is similar to Earth in size and mass. However, its surface conditions are very different. Venus has a thick atmosphere composed mostly of carbon dioxide. Clouds of sulfuric acid surround the planet. Venus experiences an extreme greenhouse effect. Heat becomes trapped in the atmosphere. Surface temperatures reach about 460 degrees Celsius. This makes Venus the hottest planet in the solar system, even hotter than Mercury. Venus has mountains, plains, and volcanoes. Many volcanic features exist. Some may still be active. The surface is hidden beneath thick clouds. radar mapping has revealed much of its terrain. Venus rotates very slowly. One rotation takes about 243 Earth days. It rotates in the opposite direction to most planets. The reasons for this unusual rotation are still studied. Earth is the third planet from the Sun. It has moderate surface temperatures. Liquid water exists on its surface. Earth has a nitrogen-oxygen atmosphere. This atmosphere supports life. Earth has continents and oceans. Plate tectonics shape the surface. Volcanoes release gases. Weathering removes carbon dioxide. These processes help regulate climate. Earth has a strong magnetic field. It is generated by movement in the liquid outer core. The magnetic field protects the atmosphere. It deflects charged particles from the Sun. Earth has one large moon. The moon stabilizes Earth's tilt. This helps moderate seasonal changes. The moon also influences ocean tides. Mars is the fourth planet from the Sun. It is smaller than Earth. Mars has a thin atmosphere. It is composed mostly of carbon dioxide. Mars has the largest volcano in the solar system, Olympus Mons. It also has a vast canyon system, Valles Marineris. Evidence suggests Mars once had liquid water. Ancient river channels and lake beds have been identified. Mars is cold. Average temperatures are about -60 degrees Celsius. Polar ice caps contain water ice and carbon dioxide ice. Dust storms can cover large regions. Mars is a major target in the search for past life. Robotic missions study its surface and chemistry. Scientists look for signs of ancient microbial activity. Mercury, extreme temperature changes. Venus, thick atmosphere and intense heat. Earth, moderate climate and liquid water. Mars, cold and dry with evidence of past water. These planets show how different outcomes can arise from similar beginnings. They provide insight into planetary formation. They show how atmospheres evolve. They help scientists understand Earth's uniqueness. They serve as reference points for rocky exoplanets. Between the orbits of Mars and Jupiter lies a broad region of space. This region contains countless rocky objects. It is known as the asteroid belt. Rather than a dense field of debris, the asteroid belt is mostly empty space. Individual asteroids are separated by large distances. The asteroid belt formed from leftover material from planet formation. Early in the solar system's history, rocky material orbited the young Sun. Gravitational influence from Jupiter prevented this material from forming into a planet. Instead, the material remained as many smaller bodies. These objects became asteroids. Asteroids are rocky or metallic objects. Most are irregular in shape. Some are only a few meters wide. Others are hundreds of kilometers across. They orbit the Sun in predictable paths. Asteroids vary in composition. Some are rich in metal. Some contain silicate rock. Others include carbon-rich material. These compositions reflect conditions in the early solar system. Ceres is the largest object in the asteroid belt. It is classified as a dwarf planet. Ceres is about 940 kilometers in diameter. It is large enough to be nearly spherical. This shape results from its own gravity. Ceres contains water ice. It may have a subsurface ocean. Bright salt deposits appear on its surface. These suggest past or present geological activity. Ceres represents a bridge between asteroids and planets. A dwarf planet orbits the Sun. It is round in shape. It has not cleared its orbital neighborhood. This distinguishes dwarf planets from major planets. Several dwarf planets exist in the solar system. Beyond the asteroid belt, many small worlds exist. Some orbit among the outer planets. Others reside in distant regions. These objects preserve early solar system material. Meteoroids are small fragments of rock. They are smaller than asteroids. When they enter Earth's atmosphere, they produce streaks of light. These streaks are called meteors. If material reaches the ground, it is called a meteorite. Small bodies are time capsules. They formed early. They have changed little. They preserve chemical information about solar system origins. Scientists study them to understand planetary formation. Most asteroids orbit the Sun in stable paths. Some have orbits influenced by Jupiter. These gravitational interactions can shift orbits. Occasionally, objects move into inner solar system paths. Some asteroids pass near Earth's orbit. These are called near-Earth objects. Most pose no danger. Astronomers track their motion carefully. Predicting orbits improves planetary defense. Throughout history, asteroids have collided with planets and moons. These impacts create craters. Earth's surface shows evidence of past impacts. Most large impacts occurred billions of years ago. The asteroid belt evolves slowly. Objects collide occasionally. Fragments break apart. New orbits form. These changes occur over immense time. Many small icy bodies orbit farther from the Sun. Some belong to distant populations. These regions will be explored in later episodes. Small worlds exist throughout the solar system. Asteroids, rocky and metallic. Meteoroids, small fragments. Dwarf planets, round and larger. Each category reflects size and gravity. Spacecraft have visited asteroids. Samples have been returned to Earth. These samples reveal ancient chemistry. Future missions will continue exploration. The asteroid belt contains many small rocky worlds. It formed from leftover planetary material. Ceres is the largest object in this region. Small bodies preserve early solar system history. Their study helps explain how planets formed. Beyond the asteroid belt lies a region dominated by large planets. The first two giants are Jupiter and Saturn. These planets are known as gas giants. They are much larger than the inner rocky planets. They are composed mostly of hydrogen and helium. They do not have solid surfaces like Earth. In the outer solar system, temperatures were low during formation. Ice and gas could remain stable. Large planetary cores formed from rock and ice. These cores attracted vast amounts of gas. Over time, thick atmospheres developed. This process created Jupiter and Saturn. Jupiter is the largest planet in the solar system. Its mass is more than twice that of all other planets combined. Jupiter's diameter is about 143,000 kilometers. It is made mostly of hydrogen and helium. Jupiter's atmosphere is layered. Cloud bands circle the planet. Different bands move at different speeds. Strong winds flow through these layers. Wind speeds can exceed 600 kilometers per hour. Jupiter contains a massive storm known as the Great Red Spot. This storm has existed for at least 300 years. It is larger than Earth. The storm rotates slowly. It is powered by internal heat. Below the clouds, pressure increases rapidly. hydrogen becomes liquid. Deeper still, hydrogen behaves like a metal. This metallic hydrogen conducts electricity. It generates Jupiter's powerful magnetic field. Jupiter has the strongest magnetic field of any planet. It creates intense radiation belts. This field influences Jupiter's moons. It also interacts with the solar wind. Jupiter has dozens of moons. 4 large moons are known as the Galilean moons: Io, Europa, Ganymede, Callisto. These moons are diverse. Some are volcanic. Some contain subsurface oceans. They will be explored in a later episode. Saturn is the second largest planet. It is similar in composition to Jupiter. Saturn is known for its ring system. The rings are made of ice and rock. They orbit Saturn in a thin, flat disk. Saturn has cloud bands. Winds are strong. Storm systems occur. Saturn's atmosphere appears calmer than Jupiter's. However, powerful storms can still form. Saturn contains layers of hydrogen and helium. Its core is likely composed of rock and ice. Metallic hydrogen may exist at depth. Saturn also generates a magnetic field. Saturn has very low density. If placed in a large enough ocean, it would float. This reflects its high gas content. Saturn's rings extend hundreds of thousands of kilometers. They are extremely thin. Individual ring particles range in size. Some are tiny grains. Some are large chunks of ice. The rings may be relatively young. Both Jupiter and Saturn emit more energy than they receive from the Sun. They slowly release heat from their formation. This internal heat drives weather patterns. Gas giants do not have solid ground. Pressure increases gradually with depth. There is no clear surface boundary. Matter becomes denser toward the center. Gas giant atmospheres contain hydrogen, helium, methane, ammonia, water vapor. These gases create cloud layers. Chemical reactions shape cloud colors. Jupiter's strong gravity influences many objects. It deflects comets and asteroids. This may reduce impacts in the inner solar system. Jupiter acts as a gravitational shield. Both are massive. Both are hydrogen-rich. Jupiter is larger and denser. Saturn has more prominent rings. Both are important to solar system stability. They shape orbital patterns. They influence small body populations. They provide laboratories for atmospheric physics. They help scientists understand giant exoplanets. Spacecraft have studied Jupiter and Saturn. Orbiters and flybys collected detailed data. Future missions will continue investigation. Knowledge increases steadily. Beyond the gas giants lie 2 large planets, Uranus and Neptune. These planets are known as ice giants. They differ from Jupiter and Saturn in composition. They contain larger proportions of heavier elements. They are rich in substances called planetary ices. In planetary science, ice refers to compounds that are solid at low temperatures. These include water, ammonia, methane. Inside ice giants, these materials exist in hot, compressed forms. They are not frozen like household ice. They exist under extreme pressure. Uranus is the 7th planet from the Sun. It has a pale blue-green color. The color comes from methane in its atmosphere. Uranus has an extreme axial tilt. It is tilted about 98 degrees. This causes the planet to rotate on its side. Because of its tilt, Uranus experiences extreme seasons. Each pole can face the sun continuously for decades, then remain in darkness for decades. Seasons on Uranus last about 21 Earth years. Uranus has cloud layers. Winds blow at high speeds. Temperatures are very low. Uranus is one of the coldest planets in the solar system. Its upper atmosphere reaches around -220 degrees Celsius. Uranus has a small, rocky core. Above the core is a thick layer of water, ammonia, and methane. Above this is a hydrogen-helium atmosphere. The interior produces little excess heat. This is unusual compared to other giant planets. Uranus has a faint ring system. The rings are dark and narrow. Uranus has many moons. Some are icy. Some show evidence of geological activity. Neptune is the 8th planet from the Sun. It is slightly smaller than Uranus. It has a deeper blue color. Methane absorbs red light. This creates the blue appearance. Neptune has the fastest winds in the solar system. Wind speeds can exceed 2,000 kilometers per hour. Large storms form in its atmosphere. Dark storm systems have been observed. These storms can appear and disappear. Neptune has a rocky core. Above this lies a thick icy mantle. Above that is a hydrogen-helium atmosphere. Neptune releases more internal heat than Uranus. This heat drives weather activity. Both Uranus and Neptune have magnetic fields. Their fields are tilted relative to their rotation axes. The magnetic centers are offset from the planetary centers. This creates complex magnetospheres. Neptune's largest moon is Triton. Triton orbits in a retrograde direction. This suggests Triton was captured. Triton has nitrogen geysers. It may contain a subsurface ocean. Neptune has faint rings. They contain clumps of material. The rings are thin and dark. They are difficult to observe. Uranus orbits at about 19 astronomical units. Neptune orbits at about 30 astronomical units. Sunlight is weak at these distances. Temperatures remain extremely low. Both are ice giants. Both contain thick, icy mantles. Neptune is more active. Uranus is colder and quieter. Both represent a distinct planet class. Many exoplanets fall into size ranges similar to ice giants. Studying Uranus and Neptune helps interpret distant worlds. They serve as local examples. Only one spacecraft has flown past Uranus and Neptune. Voyager 2 collected most existing data. Future missions are planned. Knowledge remains limited. They expand understanding of planet types. They bridge gas giants and smaller planets. They inform models of planetary formation. Many planets in the solar system are orbited by moons. Moons are natural satellites. They range from small rocky bodies to large, complex worlds. Some moons are larger than the planet Mercury. Each moon follows a stable orbit around its parent planet. Moons form in several ways. Some form alongside their planet from the same disk of material. Some form from debris created by large impacts. Others are captured objects that were once independent. These different origins explain the wide variety of moons. Earth has one large moon. It formed early in Earth's history. A large impact likely created debris that combined into the moon. The moon stabilizes Earth's axial tilt. This stabilizing effect reduces extreme climate variation. The moon also causes ocean tides. Many moons are tidally locked. One side always faces their planet. This occurs because gravity slows rotation. Tidal locking creates permanent near and far sides. This is common throughout the solar system. Jupiter has dozens of moons. 4 are especially large: Io, Europa, Ganymede, Callisto. These are known as the Galilean moons. Each has unique characteristics. Io is the most volcanically active body in the solar system. Hundreds of volcanoes erupt continuously. This activity is caused by tidal heating. Jupiter's gravity flexes Io's interior. Heat builds up, rock melts, volcanoes form. Europa is covered by a thick layer of ice. Beneath the ice may be a global ocean. This ocean is kept liquid by internal heating. Europa's ocean may contain more water than Earth's oceans. Europa is a major target in the search for life. Ganymede is the largest moon in the solar system. It is larger than Mercury. Ganymede has a magnetic field. This is rare for moons. It may contain layered oceans beneath its surface. Callisto is heavily cratered. Its surface has changed little for billions of years. It may contain a subsurface ocean. Callisto provides insight into early solar system conditions. Saturn also has many moons. 2 are especially important: Titan, Enceladus. Titan has a dense atmosphere. It is rich in nitrogen. Methane clouds and rain exist. Liquid methane rivers and lakes flow on the surface. Titan contains complex organic chemistry. It may have a subsurface water ocean. Enceladus is small but active. Jets of water vapor and ice erupt from its south pole. These jets indicate a subsurface ocean. Heat from tidal forces drives activity. Enceladus is another key target for life studies. Uranus has many icy moons. Some show evidence of geological change. Surface fractures suggest past internal heating. These moons are cold and distant. Neptune's largest moon is Triton. Triton orbits backward. This suggests it was captured. Triton has nitrogen geysers. It may contain a subsurface ocean. Mars has 2 small moons, Phobos, Deimos. They are irregular in shape. They may be captured asteroids. Small moons exist around many planets. Moons show that small worlds can be complex. They contain oceans, atmospheres, and geological activity. They expand possible locations for life. They help scientists understand tidal heating and orbital dynamics. Some moons may be better candidates for life than planets. Subsurface oceans provide protection from radiation. Chemical energy sources may exist. These environments are stable over long periods. Spacecraft have visited many moons. Orbiters and landers gather data. Future missions will focus on Europa and Enceladus. Knowledge grows gradually. Moons are diverse and widespread. They form in multiple ways. Many contain ice, oceans, and active geology. They play a central role in modern planetary science. Beyond the orbits of the major planets lies a vast region of space. This region contains icy objects, small worlds, and the outermost remnants of solar system formation. It represents the distant edge of the Sun's domain. Neptune is the outermost major planet. Beyond Neptune, sunlight is extremely weak. Temperatures are very low. Objects in this region move slowly. Orbits can take hundreds or thousands of years. The Kuiper belt is a broad, disc-shaped region beyond Neptune. It begins around 30 astronomical units from the Sun. It extends outward to about 50 astronomical units. The Kuiper belt contains many icy bodies. These objects are leftovers from planetary formation. Kuiper belt objects are made mostly of ice and rock. They contain water ice, methane ice, ammonia ice. Some are only a few kilometers across. Others are large enough to be round. Several dwarf planets reside in the Kuiper belt. Pluto is the most well-known. Others include Haumea, Makemake, Eris. These worlds are spherical due to their gravity. They have complex surfaces. Some have thin atmospheres. Pluto orbits in the Kuiper belt. It has mountains made of ice. It has plains of frozen nitrogen. It has a thin atmosphere that expands and collapses with its orbit. Pluto also has several moons. Its largest moon is Charon. Beyond the main Kuiper belt lies the scattered disk. Objects here have elongated orbits. They may travel far from the Sun and then return. These objects were likely disturbed by Neptune's gravity. Comets are icy bodies. They contain ice, dust, and rock. When a comet approaches the Sun, ice begins to vaporize. This creates a glowing coma. A tail forms. The tail always points away from the Sun. Short-period comets originate mainly from the Kuiper belt. They orbit the Sun in less than 200 years. They return repeatedly. Each pass slowly erodes the comet. Long-period comets originate from a much more distant region. This region is the Oort cloud. Their orbits can take thousands or millions of years. The Oort cloud is a vast spherical cloud surrounding the solar system. It begins thousands of astronomical units from the Sun. It may extend up to 100,000 astronomical units. The Oort cloud contains trillions of icy objects. Objects in the Oort cloud are extremely distant. They move very slowly. Sunlight is almost non-existent. Temperatures are near absolute zero. This region represents the outer reservoir of comets. The Sun's gravity weakens with distance. Eventually, the Sun's influence blends with that of nearby stars. There is no sharp edge. The solar system gradually fades into interstellar space. The Sun emits a constant stream of charged particles. This forms a bubble around the solar system. This bubble is called the heliosphere. It shields the solar system from some cosmic radiation. The heliopause is the boundary where solar wind pressure balances interstellar wind. Beyond this boundary is interstellar space. Spacecraft have crossed this region. Measurements confirm the transition. Interstellar space contains gas, dust, magnetic fields. It is extremely sparse. Objects travel vast distances between stars. The solar system is not unique. Other stars have their own outer regions, other Kuiper belts, other comet clouds. Planetary systems extend far beyond visible planets. Objects in the outer frontier change slowly. Orbits evolve over millions of years. Collisions are rare. Most objects remain undisturbed for immense periods. This region preserves ancient material. Only a few spacecraft have visited the outer regions. Flyby missions provide brief glimpses. Future missions may explore further. Knowledge grows gradually. Beyond Neptune lies the Kuiper belt. Farther still lies the Oort cloud. Comets originate from these distant reservoirs. The solar system gradually transitions into interstellar space.